begin with a word of prayer. I guess I probably should put on the microphone. Duh. Let's see here. So I'll begin. Dear Father, we thank you for this opportunity just to meet together and study your creation. Again, Lord, I just pray that you'd bless our work here today, Lord. In your name I pray. Amen. Let's see here. So you guys should probably go ahead and turn in your homework. You just pass it to the right. So we have one more of these. Zip. Oh, you guys get in yours? It's up there already? Yay. So I hope these were manageable. Were these pretty understandable given our discussion in previous classes, or nothing too surprising, I hope? So I picked out 20 more problems for the next mission. It'll be due next Tuesday. I think with that, you should be pretty much ready for my test. So, which is when? Whenever it says on the course planner. It's like after fall break, I think. But don't hold me to that. I'll have to look. I think it's the after fall break. But okay, so let's see. I've started talking about the Cauchy Euler problem. We keep talking about that a little bit. And I'm mostly doing n equals to 2. All right, so the problem basically we're studying is how do you solve something like ax squared y prime prime plus bx y prime plus cy equals to 0, where a, b, and c are constants, all right? A non-zero, of course. And so what did we find last time that we were looking at this problem? We figured out if we plug in x to the r, right? If we use a solution of the form y equals x to the r, if we make that our guess, then that implies that we need a r times r minus 1 plus br plus c equals to 0. So this is sort of the, I mean, it's not sort of, it is the characteristic equation for this problem. All right, so it's a little bit different, right, than the constant coefficient problem we worked before, but at the same time, not so different, right? Now, once you find two linearly independent solutions, if we had, instead of 0, if we had some force on the other side of the equation, we could solve it by variation of parameters, all right? So, let's see here. But just as an example, let's think about what happens if we have something like, let me see if I can make this work out right. X squared y prime prime plus xy prime plus y equals to 0. So let's see if we could we solve this one. Let's see what's missing from my previous discussion. All right. So let's see here. Our characteristic equation, we plug in, basically just plug in y equals x to the r, and after a little bit of differentiation, what do we get? We get r times r minus 1 plus r plus 1, all of that times x to the r, if you think about it, equals to 0, right? So that implies, of course, that r squared plus 1 has to be equal to 0. Now, last problem we worked, I think we had like r equals minus 1 and r equals 2 or something like that, right? Or minus 1 and minus 2, I forget. I know we got Luke's reciprocal function, and we got maybe 1 over x squared too, I forget. Because do you remember? Yeah. Anyway, my point is the problem we worked last time, the characteristic equation worked out to have real distinct roots. How about this? What is the solution to this? plus or minus I, right? Yeah. So what do you do? Is the algebra wrong in this case? No, you just have to be a little bit more open-minded about how we define functions with complex arguments and so forth, all right? So with just a little bit of common sense complex variables, we can solve this. So the solutions are something like y equals x to the I. All right, we're assuming x is greater than 0, okay? Now, what does that mean? Well, this is essentially a definition, all right? But here's what that's going to mean. This is going to mean exponential of the natural log of x to the I. Technically speaking, it's not really the natural log I'm using here. It's really the complex logarithm. But, I'll just call it natural log for the sake of in here. I probably should write, instead of ln, I should probably write log there. But, it's okay. Anyway, so this is still not really the definition. The definition is this. It's e to the I ln of x. So this middle is just a guiding heuristic, okay? No one ever defined for you what x to the I meant before, right? So I'm doing that now. It means e to the I log x. Now this has meaning for us because we already know what e to the I theta means, right? So e to the I log x is simply what? It's simply cosine of the natural log of x plus I times the sine of the natural log of x. So corresponding to this imaginary, or if you like, to take a slightly broader view, complex characteristic value, we find a complex solution, x to the I. This single complex solution has within it two real solutions. All right? So you can check it. We'll check it here. But this equation right here, this is why this function, cosine of log x, and over here, sine of log x, these are separately real solutions to the given differential equation. If you're a glutton for punishment, we could actually differentiate these and see that they work. Tell you what, I'll suffer through it. y1 prime is minus the sine of the log x over x. And y1 prime prime is 1 over x squared sine log x minus cosine log x over x squared. So if you look at that, x squared y1 prime prime plus x y1 prime, let's see, what's that equal to? That's sine log x minus cosine log x plus, let's see here, x y1 prime minus sine log x, right? So the sines cancel, right? And you're left with minus cosine log x, which is what? y1 was cosine log x, right? So we've got minus y1. So you look at that. What's that say? We've got x squared y1 prime prime plus x times y1 prime equals to minus y1, which is the same as saying it's a solution over here to star star. Okay. So it works, right? This complex voodoo mathematics I'm doing, whatever you want to call it, it's legitimate, right? I would argue it's natural. Right. Again, if you want to study complex power functions with more care and a larger discussion of it, to put it in its proper place with much more blah, 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 you should take complex analysis here, right? But there should be plenty here to keep you on track. So what's the solution then? Getting to it, therefore, y equals c1 cosine log x plus c2 sine log x is the general solution, going back to the fundamental existence and uniqueness stuff we talked about, right? If we have two linearly independent solutions, we take a linear combination of them. That forms the solution to the homogeneous problem. Now, of course, if I replace this 0 with some function, we could solve that problem with variation of parameters, right? If we wanted to. I'm not sure I want to. I'll leave that for another day. We could do that some other day. How about that? Any questions about this? So do you understand what to do if we get a complex value in the characteristic equation? We do like this. Now this one's pure imaginary. Maybe I should do one more example. Let's see here. How could I change this example so that we ended up with something like, you know, suppose I want to change this to get like 2 plus or minus I. How should I change it? Here, I'm going to show you the man behind the curtains here for a second. So this would come from r minus 2 quantity squared plus 1, right? Which would be r squared minus 4r plus 4 plus 1, which would be r squared. Let's see here. So that would be r times r minus 1. And what am I left with? Minus 3r plus 5, right? So if I've reverse engineered this properly, so you guys are preparing for careers battling China, right? So it's important to understand reverse engineering. Let's see here. Sorry. You know, I guess I'm a Trump supporter. It's kind of obligatory. Let's see here. Minus 3. I think if I do this adjustment, then that's going to give me the kind of complex characteristic values that I'm looking for. All right, now that I've made up the new problem, let's work it out, right? Ay, ay, ay. Oh. Okay, so my characteristic equation is r times r minus 1 minus 3r plus 5 equals to 0 by the usual calculation here. And that gives me r squared minus 4r plus 5 equals to 0. Complete the square. That's r minus 2 quantity squared plus 1 equals to 0. And once I've completed the square, I can read off the complex solution. R is equal to 2 plus or minus I. Well, what do you know? All right, so there we go. The question is, how do we interpret the solution then in this case? So I'm looking at y equals to x to the 2 plus I. Okay. So the way this is defined, all right, is that this is simply x squared times x to the I. This makes sense, by the way, because we were looking at x greater than 0. There's a larger discussion in complex analysis. X, like z to a complex power, is generally not a single thing. It's a set of values. But if we assume x is greater than 0, if the base is real, those ambiguities get washed away, and what we're doing is unambiguous. If this is intriguing to you, well, okay, I'm probably telling you should take complex analysis. But anyway, whatever. So x squared, and this is just what we said it was before. This is the cosine of the natural log of x plus I times the sine of the natural log of x. So basically, we're left with something like x squared cosine log x plus I x squared sine log x. And so we've got a complex solution. The real part and the imaginary part are separately real solutions to the problem. So my general real solution has the form y is equal to c1x squared cosine log x plus c2 x squared sine log x. There you go. Now, I don't want to reverse engineer the problem, but I think it's worthwhile for me to just give you like one more comment about how these, x to a complex power, what's it look like. So maybe you guys can actually help me out. Before I do that, though, I get carried away sometimes. Are there any questions? Yeah.
Could you go over real fast why we put the x is greater than 0? Is it just for the ln?
Yeah, for the log. Right, if I had x, I could also do this for x less than 0. Everywhere I have x, I'd replace with minus x. Or if you like, you could just take absolute value of x in these formulas, and then you'd have a formula which works for either positive or negative x, but not x equal to 0. X equal to 0 is what's known as a singular point in this differential equation. Full disclosure, this is actually an example of a regular singular point. This is sort of the most basic case of the Frobenius method. But we don't need that larger discussion of Frobenius method just yet. I think it's helpful to have this example alongside the constant coefficient case because it gives us another example where there's sort of like a canned method to find a fundamental solution set. So these are really the two major examples I know. I mean, I can create other examples, but they're just kind of artificial. For example, I could let t equals to x squared ddx like this, and then I could look at basically any polynomial in t acting on y equals to 0. That would define a differential equation. For example, if I had like t minus 3 times t minus 2 acting on y equals to 0, well, that would be a second order differential equation. And I could figure out what the solutions were because I can solve these separately, right? But how would you solve even one of these separately? You'd have to solve something like, x squared ddx minus 3, for example, times y equals 0. Of course, you guys know how to do that. That would be x squared dy dx equal to 3y. So you could play with like polynomials and some other operator, and you could come up with sort of the characteristic equation for that other problem and go from there. But I don't know. I don't see those things in applications, and as much as I would love to play with this, I don't think it's really part of the course. So I'm behaving and not doing it. Really, all the Cauchy Euler problem though is the Cauchy Euler problem is just taking t equals to x ddx, and the constant coefficient is in some sense really just taking t equals to ddx. So you could look at other things, and there's a similar theory of how to solve it, and there's a different characteristic equation and so forth. Provided that you can actually write your differential equation in terms of a polynomial of a singular operator. Not all differential equations work like that. There are problems where it could be that the differential equation is formed from the composition of two operators which don't commute and can't be, well, I don't know. I mean, that seems like a really strong thing to say, that I cannot rewrite them as a polynomial in some operator. I'm not sure, honestly, guys, to what extent it's possible to rewrite an arbitrary differential equation in terms of polynomial in a given operator. I don't see theorems about that in your book. But now I'm digressing. All right. Bonus stuff aside, Where was I? Oh, one more example, just to make sure we understand each other. What if I had y equals to x to the, say, 3 plus 2i? How would this work? You do x cubed, x to the 2i, right? And here, just I'll put in my guiding heuristic. That's the exponential of the log of x to the 2i. And basically, we define the law of the law of exponent to work. So we got x cubed cosine of 2 log x plus I x cubed, the sine of 2 times log x. And so that's how that one would work. Okay. Are we clear? All right. Now, there is an obvious other case, though, right? What about when the root is repeated? Right? So, what would you do if you have something like, I'm going to have to work backwards again. If you have something like r squared minus 4r plus 4, right? That would have been r times r minus 1 minus 3r plus 4, right? Okay, so I figured it out. If I just change this 5 to a 4, that happens to us. Ah, cool. Man, look at that. Just change that by 1 unit. It's a totally different problem. You have some homework like that in your next one, where you actually take a given differential equation and you study what happens by just changing one of the numbers in the differential equation, how the solution changes, right? Physically speaking, that's important, right? Because these parameters in the differential equation correspond to things like, like a spring constant, right? Or a damping coefficient or something like that. Or it could be the resistance or the inductance or capacitance in a circuit. And it's kind of interesting to think about what would happen if everything else being the same and I changed just one of those things. Right? So some of your homework is actually about that idea. Those problems are tedious, but you can use graphing software. You don't actually have to hand-to-hand combat those graphs if you want to. You could just use Mathematic or MATLAB or Wolfram Alpha, whatever, print it out and stick it in there. It's fine. Ay, ay, ay. Excuse me. So you guys, what's the characteristic equation there? I came prepared, sort of. Okay. So we got ourselves r times r minus 1 minus 3r plus 4 equals to 0. That gives me r squared minus 4r plus 4 equals to 0. That factors to r minus 2, quantity squared, equals to 0, right? So then what? Well, one solution, so that means r equals to 2, right? 2 times. So on the one hand, we get y1 equals x squared, right? But we know from the theory that we should get 2 linearly independent solutions for a second order problem, right? There should be a fundamental solution set. There should be 2 linearly independent solutions. Without those 2 linearly independent solutions, we'd have trouble solving, for example, if I stick a forcing function here, I need the 2 linearly independent solutions to start variation parameters, right? We know there's something missing. Where is it? Right? Where is it? So I'm going to show you something, and I'm actually going to have the good sense to not actually work it out. I'm just going to show it to you. Every so often I actually work this out hand-to-hand combat, and it's not a bad thing. It kind of depends on how the course went. We've done a lot of other calculations in here, so I don't feel obligated to do it. And I couldn't, for the life of me, I couldn't find it in your book. So I don't know where I found this thing. I mean, it's not just me. Dr. Skambordis knows about it. So maybe it's one of the other books we've taught from over the years. I don't know where I found this thing. I feel like it was in this book, but I cannot find it. I looked at old editions. I still can't find it there. So I don't know where I found this stupid thing. But I will tell you this. Generally speaking, these differential equations books have got dumber and dumber and dumber with every edition. If you look at a third edition of this book, you'll find a deeper and more substantial book. All right, come on. All right, come on. You guys have a good weekend? Oh, the debate. Yeah, I don't know. That debate was fun. I mean, I cannot remember. I mean, it would be fun to just go back and like watch 5 minutes of a Romney debate and just contrast. Like, just, I mean, there were many things that were missed. Like, come on, how can you not bring up her email when you're talking about cybersecurity? I mean, how can you not bring up the email? And then, like, she's talking about, like, ancient history with what Trump did to this person and that person in the 70s. He ought to be, like, throwing Rose Law Firm interface and, like, you know, Travelgate and stuff that everybody's forgotten about. You know, because you got 30 years of controversy after controversy after controversy with Grandma there. So, I mean, I don't know. Kind of disappointing. But, generically speaking, very feisty, and I was not surprised, really. I was just, I mean, I've been looking forward to this for some time. It's the silver lining to my guy not getting it. And I still think he's going to win in a landslide. He's saying things people have wanted someone at that level to say for a long time. And I know the media is embarrassed that people actually believe these things, but people do believe these things because their jobs are gone and so forth. So whatever. I think I've got to digress from math a little bit. My apologies. So here is a really interesting formula that we don't teach you in calculus, but we ought to. There is an n-fold. Is that a B? What? That's supposed to be an n. I don't know where that came from. All right, so the n-fold, the nth derivative of a product of two functions, you can actually write in terms of binomial coefficients like so. This is the generalized product rule. So like, for example, at second order, it says that the second derivative of f times g is like f prime prime g plus twice f prime g prime plus f times g prime prime. And this goes on. Like the third derivative of a product would be f triple prime plus 3 times f prime prime g plus 3 times f prime g prime prime plus g prime prime prime. And so forth and so on. It's binomial. Anyway, you can use these things, all right? And you can take the nth order problem, and basically you can make a substitution that you make a substitution z is equal to v prime. What is v prime? I think that's supposed to be y prime. Oh, I don't know. Anyway, you make a substitution and you can cut the order of the thing down by 1. All right, basically you can remove the 0th thing by making up something called you call a variable the derivative, and you end up with a problem of n minus 1th order. Now, let me just get to the problem here. Let me be more specific. So if you do this for the second order problem, here's how it goes. Suppose we got a second order problem, ay prime prime plus by prime plus cy equal to 0. Here a, b, and c could be functions, right? So in other words, a could be like ax squared, b could be bx, c could be c. It could be the Cauchy Euler problem. So you have a solution, all right? Suppose you've got a solution, y1, like we do here. We've got one solution, but we don't have a second one, all right? Then you can make a substitution. You can substitute y2 is equal to v1, vy1 The reason that this is with the reduction of order stuff is it's a very similar idea if you dig through the calculations on the last page. I don't expect you to really. Okay, it's a little bit beyond the standard course these days. So anyway, so y2 equals vy1. You differentiate the product, right? And that will give you like v prime y1 plus v y1 prime, you know? And the second derivative gives you this. I'm using that Leibniz product rule for like the second derivative. There it is, you know? So this v is playing the role of big F, and y1's playing the role of big G from the previous page. And so there you go, plug it in. What happens? Well, you know ay1 prime prime plus by1 prime plus cy is 0. So that means that this guy, that guy, and this guy go away, just like in various parameters calculation we did, right? Very similar to that. And you're left with things that have derivatives in the v. All right? Now, the reason this, why would you expect, what's the whole idea here? We're trying to find a linearly independent solution, y2, right? So what does that mean about the v? You're searching for a v such that what? V is not constant, right? If v is a constant, then that would just be a scalar multiple of y1, which we already have. The theory that we went over before says that there exists such a y2, which correspondingly means there has to be some function v, which is not a constant, such that you can write y2 is equal to vy1. So this is a reasonable guess to make on the basis of linear independence, what we're looking for. It's not quite as madcap a guess as some of the things we've done in here. Anyway, so plug it in and you get this, all right? Well, the cool thing about this equation, right, is there is no just plain old v, right? There's v prime, there's v prime prime. So if we make a z equals v prime substitution, it's straight up linear in the z variable. And then this y1 is something we already know. The derivative of y1 we also know. Integrating factor technique solves this. Bam. And so we get v is equal to c exponential of that stuff. But remember z is that stuff rather. But remember z is dv dx. So you can integrate this to get that. All right. And then there's a sneaky thing here. If you look at this integral, that's it by change of variable. That is, if you look at that, this is the derivative of 1 over y1. I don't know if that 2 is supposed to be there. Oh, sorry. Anyway, so after a short little manipulation here, this can be rewritten simply as that. And there you go. This boxed formula is the second linearly independent solution formula. This is a calculation you can do when you have one to get the second one. Just a straight formula. I could not find that in your book for the life of me. All right. Now, just for kicks, there are actually better ways. But it is comforting, and that's a formula. We derived it, right? It's kind of cool. Let's see here. Let me try to apply this formula. y2 would be what? y2 would be what? Supposed to be the exponential. Well, y1 rather. y1, which in this case is what? X squared, the integral of what? 1 over x to the fourth for us, right? So y1 squared would be x to the fourth in our problem. And then we're multiplying by the exponential of the integral, minus the integral rather. What's my b and what's my a? A is equal to x squared in my problem. B is equal to minus 3x. So b over a is equal to minus 3 over x, right? Okay. So what is this? We have 1 over x to the 4th. This thing integrates to the 3 times the natural log of the absolute value of x. Let's just say, let's suppose that x is positive here again, to keep absolute values out of the picture. And so this is really e to the, it looks to me like that's e to the x cubed. Excuse me, just x cubed. Because we get the exponential, we get e to the 3 of this stuff, right? So what is that? That's, in other words, this piece, the exponential integral piece, is just x cubed. So we've got x cubed over x to the 4th. So that's 1 over x, right? So we get x squared log of x. There's your second linearly independent solution. All right. Now, anyway, this is my notes. I think it's an interesting formula. I think it's good for people to see it. Look here, I derive the x e to the x formula in the constant coefficient case by doing the integral just the same here. So this is another way we can understand where the x in the x e to the x formula comes from. It's from this derivation, this reduction of order derivation. I think there's a lot of different ways to understand where the x comes from. Let me show you another one. Well, any questions about this before I put it away? Yeah?
Can you just remind me, when do you use this?
This is useful in a second order problem where you found one solution, but for whatever reason you haven't found a second one. So this allows me to find a second linearly independent solution, provided I can hack my way through this monstrosity of integration, which tends to work out pretty easy for actual problems we're interested in, as it happens. But it does leave you with the question, is there a better way? Is there some sort of more simple heuristic with which I can derive the missing link here, so to speak? So let me show you another way to understand this. I'll just call this the partial lambda technique. All right. So first of all, I would point this out to you guys. We have L, right? L of y equals to 0 was our original. Let me go back to the constant coefficient case for just a second here. Right, so you got like an d to the n plus plus a2d squared plus a1d plus a naught, right? All of that acts on y to equal 0. And as we discussed, so this is my L. And we said, okay, so if we have L acting on e to the lambda x, right, we get basically what? This equals 0 if what? If an lambda to the n plus plus a2 lambda squared plus a1 lambda plus a sub naught is equal to 0, right? Great. Now there, I didn't really derive it for you, but I just said, I pointed out that if we take x times e to the lambda x, in the case that like lambda is a repeated root, it works, right? And then we prove by induction that if we have an n-fold repeated root, we get those n solutions, e to the lambda x e to the lambda x squared e to the lambda x, and so forth, right? But I didn't really derive where it's coming from. I just said it works, and I proved to you it works, and maybe that's enough, but maybe it's not. Let me show you another way we can understand where that's coming from. So another way you can understand this is by saying, okay, well, partial lambda and L is the same as L partial lambda. In other words, there is no explicit lambda dependence for the operator defining the differential equation, right? So, what does that mean? Well, if I have L of e to the lambda x equals to 0, then if you calculate partial lambda of L e to the lambda x, that will be partial lambda of 0. But what's partial lambda of 0? Well, you know what partial lambda of 0 is. It's 0, right? But on the flip side here, this is L times partial lambda of e to the lambda x. What's the partial derivative of e to the lambda x with respect to lambda? X is a constant with respect to this partial differentiation, all right? So this is L of x e to the lambda x equals to 0. There you have it. So this implies that y equals x e to the lambda x solves L of y equals to 0. There is, of course, some kind of cheat here, because the immediate thing I think of is like, so why can't we do this in the non-repeated case? Right? Because I know full well that something goes wrong with this calculation, right? I'm not, and I don't have a quick answer for you either at the moment, but if I've got something like L equals d squared plus 3d plus 1, so d plus 2. So d plus 2 times d plus 1, right? I know that I have L of e to the minus x equals to 0, but I also know that L of x e to the minus x is not a solution, right? So is something I'm cheating here, I'm not sure. Oh, maybe this is it. To be more explicit, L of lambda, I think I need to introduce a different variable, but I'm going to shut up. This is enough. I'm not going to get into it. I'd just be distracting us. I can show you after class if you're interested as to the resolution of this. Anyway, so you can see pretty much the same song and dance, right? If you have y equals x to the r as a solution, right? If you partial differentiate this with respect to the parameter, you get what? You get log of x times x to the r, if you forgot, right? We're differentiating with respect to the exponent, so the base x is fixed. Remember, if we differentiate a to the x, we get log a times a to the x. This is like that. And so there you have it again. Of course, here we derived x squared log x because r was equal to 2, but this is actually a general technique for deriving the second. In the repeated root case, we can differentiate with respect to the parameter if we have some sort of characteristic equation for the problem. Fine, I guess I'll try to explain it. I probably need to introduce another letter. It's something like so suppose P of t is like, t minus lambda squared times g of t. All right, so here I just mean, this makes p of lambda equals to 0 double root, right? Suppose you have a polynomial like that, right? Then if I calculate dp dt, what do I get? I get 2t minus lambda, right? G of t plus t minus lambda squared g prime of t by the product rule, right? So this factor here is necessary. Let's see here. So if I have L as equal to P of D, right, then partial L partial T will be exactly P prime of D, which would be 2 times, d minus lambda g of d plus d minus lambda squared g prime of d. And the point is, you can see that partial L partial T, if you take this operator, right, and you act on e to the lambda x, you get 0. Because this e to the minus lambda x is sent to 0 by that operator and that operator. If I don't have a double root, and I look at, in contrast, if I didn't have the square and I just had t minus lambda, when I look at partial t partial lambda, if e to the lambda x, I wouldn't necessarily get 0. So it's important for that to be 0 in order for this calculation over here to be legitimate. But anyway, I'm sorry, I'd have to develop more of a theory of polynomials and so forth to do this justice. I'm sorry, I should shut up about it. I've forgotten the right way to cheat the discussion. Anyway, you can see this is a heuristic method, right? If nothing else. You just partial differentiate with respect to the parameter, and that gives you the other one. Fully understanding why this works, we can leave as a future project for you or something, right? That's a harder thing. I don't think I've completely explained it. But on the flip side, I did completely explain the silly second linearly independent solution, so you can't fault me too much. And I will show you 2 or 3 more ways to find the x in the repeated root solution before the semester's done, so don't worry. All right, so that brings us to the energy lemma, which I think you guys will probably like more. Sorry to talk so much about this. I just didn't want to hurry, because your book is not terribly verbose about the Cauchy Euler problem. It's kind of relegated to problems in different sections until the Frobenius method, but I don't want you guys to read the section on the Frobenius method right now, because that's like, no, not yet. It's not time. It's not the time for it. All right, so energy lemma. So if we have a conservative force, what's that look like? What's a conservative force? If we're dealing with y as the coordinate, so if we have a net force, and then that would be equal to like minus what? du dy, that's physics, right? U would be the potential energy function, right? And so if you look at Newton's second law, which is what? Ma equals the net force, right? What does this become in the case of a conservative force? Well, this becomes m dv dt, right, equals to minus du dy, right? Or we could rewrite this as mv dv dt plus dy dt times du dy. equals to 0. I multiplied by the velocity. All right. Now, if you tilt your head and squint, you can see what we're really looking at is the time derivative of 1/2 mv squared, right, plus u equals to 0. Now there I've made an identification that I'm rewriting the potential energy as a function of time, right? Basically, I'm plugging in y as a function of t into the potential energy function, so rewrite the potential energy as a function of time. And the first thing is really just an identity. What happens if you differentiate 1/2 mv squared with respect to time? Assuming the mass is constant, this gives you 2v dv dt by the chain rule, right? Which is what we have up here, except there's no 2, but that's why the half is here. Do you guys recognize what this is? Right, this is the total mechanical energy. So you can use that to solve differential equations, in a sense. And this is what I think section 4.7 in your book, his so-called energy lemma. His energy lemma is really this, without some of the physical trappings. He's really just sort of distilled this physical result down to just a mathematical lemma. All right. And I wanted to show it to you in terms of physics instead. Let me see if I can use this as in an example to show you how we can use it to solve sort of a differential equation. How about Hooke's law, F equals minus k? We'll use y just to be consistent with the section. Okay, so if that's the force, then that means that my potential, u, is 1/2 ky squared, right? So my energy as a function of y in the the velocity v is what? It's 1/2 mv squared plus 1/2 ky squared, right? And so the theorem basically is solutions to ma equals to f, aka m y prime prime equals to minus k times y are given by level curves of the energy function. That's essentially the energy lemma. In other words, I can look at 1/2 mv squared plus 1/2 ky squared equal to, say, E naught. And that, in some regard, describes the solution to this differential equation. Now, it's not a solution, I haven't found y, right? So what kind of solution is this? It's a really different thing, right? This is the relation between the speed, or rather the velocity of the solution, the coordinate of the solution, and the energy of the solution. Of course, this is physically interesting, right? And you can even plot different solutions in something called the phase plane here. So if I draw the velocity this way, and if I draw the coordinate that way, I can plot solutions qualitatively in this so-called phase plane, right? What is this if m and k are positive? I'll start you out. Energy 0, what's the spring do? It just sits there. Now, they're not quite circles, but similar. Yeah, these are ovals or ellipses. And so basically here's some plot. Now these, again, is this a graph of solutions directly? No, right? But these things like this and so forth, these are so-called phase or Poincare plot. phase plane plot of the solution. Now, if v is positive, which way is y going? What's v? Remember, v is dy dt. So what does it say if the velocity is positive, y is going which way, right or left? In my picture. This means y is positive here, right? That's what that symbol means. So, in other words, and this means v is positive. So all of these guys are going that way, right? And down here, the other way, right? They're going left down here. This picture completely describes the physical behavior of this system. So this is why it's in that part of chapter 4. It describes some qualitative features of solutions. We can study the energy. Some differential equations we can study the energy, right? Like if I had something like y prime prime plus 3y prime plus 2y equals to 0, I'd be out of luck. This doesn't have an energy function because this right here basically is violating it. So, comparing, we're looking at my prime prime equals to minus 2y. So this would be my sort of net force, except that I've got that term too, so it's not just the net force, right? The net force is not just a function of y, which means there's no potential energy function. Because this is a friction force, and that means that energy actually is not conserved. We can go through a very similar calculation to this and find out not only is it not conserved, we can explicitly find out how it's not conserved, but we'll do that some other day. So anyway, I haven't done much in that section. I assigned you a token problem on Armageddon, which looked fun. So the idea is you've got the Earth going around the sun, right? Imagine somehow the Earth loses its angular momentum and then just goes into the sun. So the question is, how fast does it happen? And so you can do that because energy is conserved in this problem. So you can use energy. You can use energy methods. Or, if you really want to, you can solve it directly. I think separation of variables will do it. But goodness gracious, I tell you the truth. If you can use energy to solve a problem, it's usually faster. Okay? So that's why I'm talking about this for a couple minutes to kind of prep you for that problem. And that brings us to resonance. All right? All right, so let's see here. Anybody have your book? Could you let's see if I can. The main thing is I got to get started on the right letters. This is section where'd you go? How many sections on mechanical vibrations does this guy have? Goodness gracious. All right. Come on. Come on. Ah, thank you. We face the problem m d squared y dt squared plus b times dy dt plus k times y equals to f naught the cosine of gamma t. And we're assuming the underdamped case. Maybe next time I'll talk to you about the terminology here. But 0 less than b squared less than 4mk. So basically there's underdamped, there's overdamped, there's critically damped. These correspond to the three different cases we hit in the characteristic equation, right? Distinct real roots, complex roots, so forth. I think overdamped is both roots real and distinct. Critically damped is the repeated root case. Underdamped is the complex case, right? So we're looking at the